MetaScience News.
Greetings, my beloved lovers of the scientific truth. A solar neutrino transformed the carbon-13 isotope into radioactive nitrogen-13. This represents the first direct observation of a neutrino participating in a weak interaction. Neutrinos are among the most mysterious particles in modern physics. They interact with matter extremely rarely, carry no electric charge, and yet possess a small but non-zero mass. Neutrinos participate only in gravitational and weak interactions. They are produced during nuclear reactions, for example in the core of our Sun, because they pass almost unhindered through ordinary matter. Detecting them is exceptionally challenging, forcing scientists to build enormous detectors deep underground, underwater, or embedded within thick layers of ice. An international collaboration of scientists has for the first time directly observed how neutrinos transform carbon atoms into nitrogen inside a massive underground detector. This event was recorded by the SNO+ detector at SNOLAB, a leading international research facility located in the active mine near Sudbury, Canada, about 2 kilometers underground. This extreme depth shields the experiment from cosmic rays and background radiation that would otherwise overwhelm the extremely weak neutrinos signals. The results of this study were published in Physical Review Letters. Scientists were searching for events associated with the weak interaction, specifically inverse beta decay. In this process, a neutrino interacts with the carbon-13 nucleus, transforming itself into an electron and converting one of the neutrons in the nucleus into a proton. As a result, the carbon nucleus becomes nitrogen. The produced isotope nitrogen-13 is unstable and has a lifetime about 10 minutes. Physicists identified these transformations using the delayed coincidence method. They searched for two correlated signals. First, a flash produced when a neutrino strikes a carbon-13 nucleus, and then several minutes later a second flash generated by the subsequent radioactive decay of nitrogen-13. The observation of both flashes makes it possible to clearly distinguish genuine neutrino interactions from background noise. An analysis of the detector collected between May 2022 and June 2024 revealed 5.6 observed events over a total of 231 days of exposure. For the same period, the expected number of events from neutrino interactions was approximately 4.7. Despite the extreme rarity of the required carbon isotope, we were able to observe its interaction with the neutrinos that were born in the core of the Sun and traveled vast distances before reaching the detector. SNO+ experiment builds on the infrastructure of the original SNO facility, which previously demonstrated that neutrinos oscillate between three flavors: electron, muon, and tau neutrinos during their journey from the Sun to the Earth. Thank you very much for your attention. If you liked this video, please leave your like and subscribe on my YouTube channel. See you again next time. Bye bye.